All right, so aircraft construction. Can you all see my screen? Just so I know it's sharing.
You're good.
Okay, perfect. So first thing is airworthiness. So airworthiness, this is mostly going to matter when we're talking about the airworthiness certificate of an aircraft. Outside of that, really, it's just there's specific regulations that pertain to certain airworthiness types. But for the most part, this is more of a thing to deal with, how the aircraft is registered under the FAA. So this doesn't really have anything specifically to do with, you know, it does have something to do with how it flies, but this is more regulatory. So airworthiness has a lot of different categories. So, for instance, we have the normal utility, acrobatic, and commuter categories. We have, rotorcraft categories for normal and transport. Transport being, something that's used for more like commercial operations. Normal would be, you're just going out in your little aircraft and flying around. So, we have all these different categories, and each one has a specific section. So, for instance, normal rotorcraft airworthiness category is in part 27. So that's Title 14, Part 27, and you can find everything about normal rotorcraft category of aircraft. There are also specific sections that pertain to engines and propellers. So the airworthiness has three parts. Basically, it has the power plant, the propeller, and then it has like the body shape. So, how does it fly? Does it have a rotor? Does it have wings? Is it capability of acrobatic flight? Whatever. So, yeah. So those are the different parts that are associated with those airworthiness. And the FAA also issues airworthiness certificates based on these. So when we're talking about airworthiness certificates, there's really two types. There's a standard and then there's a special airworthiness certificate. In order to be certified, you have to pass inspection on the airframe, engine, and the propeller, all three of those things, in order to get an airworthiness certificate. And so a standard airworthiness certificate is issued for the normal, utility, acrobatic, commuter, and transport category aircraft. And this is going to be white. And these airworthiness certificates, just like your registration certificate, have to be displayed inside the aircraft in a place that either the crew or passengers can see these. So, not hidden away in a book somewhere underneath the flight desk, or I don't know, whatever. They have to be, somewhere in normal sight of somebody other than the pilots. And a special airworthiness certificate is going to be pink, and these are issued for primary, restricted, or limited category aircraft. And also, they have a special subtype, which is a provisionary type, which is for ferry permits and experimental aircraft. So, the special airworthiness certificate is going to be, for experimental, obviously. And also, if aircraft is like a kit built, it would also get a special airworthiness certificate, or some other type of special aircraft that doesn't fall under the standard category for some reason. And the ferry permit is just a type of permit that basically allows you to transport the aircraft from one part of the country or a state to another. It's kind of like a one-time thing for whatever reason that might be. It might be to fly it to a museum or something like that. All right, now we're going to talk about the four forces of flight and how this relates to aircraft construction. So these are not the four forces of flight. Sometimes it feels like it, but the real four forces of flight are lift, weight, thrust, and drag. And we're going to talk about these, not very in depth, but we're going to go over them enough to where we can talk about aircraft construction. So thrust and drag. Thrust is created by either the propeller or a turbine on a jet engine aircraft, and it's what counteracts the drag force. So whether the aircraft has a forward-facing propeller or a backward-facing propeller, or it has a turbine, it creates thrust in some way to push the aircraft forward or pull it forward through the air, and counteract the drag that's created. Drag has two components. So there's parasite drag and then there's induced drag. Parasite drag is caused by the aircraft moving through the air. So you can think of this as things that are sticking out from the aircraft, like antenna rivets. Yeah, I don't know, you stick your hand out the window, stuff like that. The air contacts that surface and it creates drag. So the faster you move through the air, the more drag is created by those things. And so this type of drag is known as parasite drag. The other type of drag is induced drag. And induced drag is caused by the creation of lift. So this is inversely proportional to the amount of velocity that the aircraft has. So as lift increases, your induced drag decreases. So it's the most at the point that you're just starting to make lift. And we'll talk about why this is a little bit later, but for now, I'll just have to trust me on this one. So we have parasite drag and induced drag, and the thrust force has to counteract that. And in order to accelerate, it has to exceed that drag component. So here's a graph of the parasite drag and induced drag that we were just talking about. And this is the total drag curve. If you map a line between them, if you add them up and draw a line between them, that's what you get. And these two lines where they're at their lowest point here on the graph, this little dip in the blue, or the intersection of parasite and induced drag, this is what we call L over D max. And L over D max is the point at which the aircraft is creating the least amount of drag. This speed is also referred to as the best glide speed, because you're going to be able to go the furthest with just a minimum amount of speed. So the L over D max, or the best glide speed, you usually don't fly at this speed. It's not usually very time effective. It's usually pretty slow. I think in a Cessna, let's see, it's usually around like 70 or 75 knots or something like that. And it depends on your configuration. So whether or not you have your landing gear down or flaps down or whatever. So this is just for, normal flight. That's kind of anecdotal. So the main thing we want to get from this graph, though, is we can see that the induced drag curve goes down as velocity increases, and the parasite drag curve goes up as velocity increases. And so these are kind of two things that you have to balance and keep in mind as you're flying. The other two forces of flight are lift and weight. So lift is created by the wings, and it's used to counteract the weight of the airplane. The weight is obviously created by the pull of the earth on the aircraft, and you have to counteract this force in order to leave the ground, obviously. One thing to note about the weight vector in particular is that the weight vector always points to the ground, no matter what orientation your aircraft is in. So if you're pitched up, the force vector for weight always points to the ground, and the lift vector always points perpendicular to the wing. So here's a slide that demonstrates this. So as you can see here, the lift vector points straight up, perpendicular to the wing, out of what we call the center of lift, or CL. And this is the imaginary point where the lift vector is generating the most lift, you could say. So the center point between all the lift vectors. And then the center of gravity is where the weight vector comes out of, and you have a downward component, which is the main vector. Then you also have this other side component here, which opposes the lift vector. But for the most part, it's this downward weight vector that points always towards the earth. That's going to be the strongest. And so no matter what your orientation is, it's always going to be pointing towards the ground. All right, now that we got that out of the way, we can start talking about some of the flight surfaces and how these work. So there are a lot of different sections on an aircraft. There's the empennage, which is the tail section, the fuselage, and the body. You got the wings, the power plant, and the landing gear. So these are just the main sections. There's a lot of there's a lot of subsystems like the electrical system, the brake system, stuff like that. So there's a lot of sections to an aircraft, and we're going to kind of talk through each part individually and go through, what it includes and how it works. So we'll start with the fuselage. So the fuselage is the central part of the aircraft. This is what provides the structure, the rigidity. Sometimes if you're in a pressurized aircraft, it is a pressurized vessel, so it has to be quite strong to resist crushing. This is usually where the passengers sit, the cargo. Sometimes there's even fuel, but usually the fuel is carried in the wings. This fuselage is usually constructed of either wood, steel, or aluminum. Wood, not as much these days unless you're, building a kit airplane, but a lot more it's going to be aluminum. Some are starting to be constructed using carbon fiber, but there's some challenges with that. And usually these are going to be either monocoque or semi-monocoque construction. And there's a diagram later that kind of explains what these are. Basically, it's kind of like stretching the skin around some discs, and the skin provides the resistance to the forces, and these discs kind of just provide a rigidity to the skin so that it resists crushing in and of itself. Kind of think like a tin can with like baffles inside of it or something. So quite strong and a lot better than some of the other types that are out there. So fuselage, main part, passenger people, usually constructed out of wood, steel, aluminum. So attached to the fuselage in some way is going to be the wings. And the wings, again, are the part of the aircraft that creates the lift that you need to counteract weight. And because of this, they need to be quite strong. But they can't be too rigid, because if they're rigid and strong, if you hit turbulence, that could break the wings. So you don't want that. So they have to be kind of flexible. And I don't know if you've seen videos out there, but some of the larger aircraft like the 787 and stuff, they have pretty impressive wing flexes. They're able to curve quite a bit. And this is important, especially when you're carrying a lot of weight. You have to have a wing that can accommodate that without breaking or shattering. So they have to be quite strong and they have to be quite flexible. So very unique characteristics. Wings usually are located either the top, middle, or bottom of the aircraft. So like in a Cessna, you're going to have a high wing aircraft, so they're at the top, and they have spars connecting from the bottom to the top to provide rigidity so that they don't break. And then you have something like Beechcraft Bonanza, where the wings are at the bottom of the aircraft, and these don't need any bracing because when they attach to the bottom, they have enough structure down there to support that. Mid-wing aircraft, there's some jetliners out there, Boeing jets, mid-wing aircraft sometimes. I can't think of any in particular off the top of my head, but the wing comes out of the middle of the aircraft instead of the bottom of the top. So high wing aircraft, like I said, usually have bracing to provide structure support to the wings. Actually, it's kind of interesting. One of the first planes that Cessna made was one where it didn't need any spars. It doesn't need the spars to fly. However, there are certain points in flight that if you're pulling enough G-forces, you could damage the wings. So they're there just to provide some extra support in case you go outside the bounds. However, technically speaking, you could fly a Cessna without the spars. You just need to fly very, very carefully. Wings also are the place where the fuel is stored. So Usually it's stored pretty close to the aircraft's body, and I think there's a diagram on the next slide that shows this. And the fuel is usually carried in either rigid or a flexible container. Just depends on the aircraft design. So here's a diagram of the wing. So we have the fuel tank here, pretty close to the wing root. So this is mainly to allow for the forces to be concentrated near the center of the aircraft, since fuel is quite heavy. On the back side of the wing, this part behind the fuel tank, this orange highlighted section is the wing flap. We'll talk about flaps on the next slide. This purple part here on the outside is the aileron, and this is what allows to control the roll of the aircraft on the bank angle. So that pitches up and down to control that. Inside the aircraft wing, you have all these kind of middle sections that are the same shape as the wing. These are called ribs, and these ribs provide structural support along the wing surface, because usually the wing surface is made out of metal or carbon fiber or something else, fiberglass even. And these ribs just provide support to that frame, because the wing does have a very specific shape that it needs to keep in order to generate lift efficiently. So yeah, so it has the skin around the ribs, and those provide the strength. And then in between the ribs, there's these little stringers, which provide strength in the other direction, so that, you know, all the forces are kind of balanced between the wing. And then on the outside here, we have the wing tip. And the wing tip could have a couple of things. Sometimes wingtips have extra fuel tanks. Sometimes the wingtips, you know, have extra little flares, like winglets or sharklets. These are to help prevent wingtip vortices, which we'll talk about later. There's little things that stick up a lot of, you know, like the 737 and stuff. They have these little winglets that stick out of the wingtips, and those are there to stop airflow from going underneath to the top. And also on the wingtips are going to be your lights. So usually, you know, you have a nav light and a strobe light on the wingtip. So yeah, so that's the whole part of the wing, and usually an aircraft has two of these. Yeah, fun fact. So flaps, like we talked about on this slide, are this little orange part here. And flaps have a few different purposes. One is to help increase surface area, so that you're able to, you know, create lift at slower air speeds. But they also create a lot of drag, and this is helpful in slowing down. So you can land slower, and you can create more drag to get slower if you need to. And so there's a lot of different types of flaps. There's just none. You could just have no flaps. You could have a plain flap, like as shown here in this diagram. And the plain flap just kind of rotates around this center axis here. And it doesn't really do much. It just kind of goes up and down. Yeah, I've never really seen an aircraft that has these, but they're out there. Kit-built aircraft probably, or some other simpler designs, because this does not incorporate any other moving parts. It just rotates. Another kind of simpler design is a split flap design on the bottom left here. This just kind of pops out of the bottom of the wing, and yeah, this is primarily for creating more drag. It does create a little bit more lift as well, as it increases that camber, but yeah. So split flap, again, that's kind of something you'd see more on a kit built. Some of the older planes also had split flaps, but usually today it's either going to be a slotted flap or a Fowler flap, or it's going to be a combination of those. So most Cessnas have what are called Fowler flaps, which instead of just moving down like a plain flap does, the Fowler flap also moves backwards. And this allows air to flow up and around the Fowler flap, and it acts kind of like a second wing. And so you get a little bit more lift, you get a little bit longer wing to create that little bit extra that you need. And same thing with a slotted flap. The slotted flap allows air to move up and around inside and create more lift in there. And then, you have the combination of the two, which usually this is more for larger aircraft. They have a slotted Fowler flap or a doubly slotted Fowler flap, or, even more Fowler flaps. So, yeah. So yeah, like I said, they are used to generate lift. So the air flows up and around them, or it increases the camber so that you can generate more lift at a slower airspeed. The empennage of the aircraft is the tail section. And this has a lot of different parts on it. It has your rudder, which is used to control the yaw of the aircraft. It also has the elevators, which are used to control the pitch of the aircraft. And then it has some other stuff. So it has trim tabs, sometimes for the rudder and the elevators. There's a couple different types of trim tabs, but these are used to control what the effect of that control surface is like at neutral. So if you let go of the sticks and your rudder pedals and you just let it fly, what does it do? And so you can set these so that it flies straight and level for a given airspeed. I don't know, you pick 90 knots or 100 knots or something, and you set that so that at 100 knots or 90 knots, if they're set at 0, it flies perfectly straight. Also, there is usually some static wicks on the backside and some lights, but these are part of different groups, so we won't really talk about those. So yeah, we have the elevator, and that elevator is on what we call the horizontal stabilizer, and then we have the rudder, which is on the vertical stabilizer of the aircraft. And as it turns out, there are a lot of variations to this design, such as the stabilator, the T-tail, the V-tail, and the split tail. What I find most interesting here is the stabilator design. It basically takes the entire elevator control surface and turns it into one thing that moves up and down. So instead of having two flaps on each side that move up and down, you have this whole long bar that moves up and down at the same time, which is kind of cool. And it also has this really long trim tab on it. So it's kind of a unique design. But I also like the V-tails. I've flown one of these before. They're very interesting in how they handle. A lot different than a normal aircraft. Kind of takes some getting used to. So yeah, each of these has its own characteristics and how it performs and its own problems. So yeah. Any questions so far on any of the stuff we talked about? Cool. All right. So the landing gear. The landing gear obviously support the aircraft when it's on the ground. So in flight, usually they're either retracted if it's retractable, or if they're fixed, they just stick out there. Sometimes manufacturers will include coverings for the wheels so that they don't generate as much drag, or they make them retractable. There's a lot of different types of landing gear. So you got like your skis, floats, tail wheel, tricycle gear, a lot of different variants out there. Sometimes the nose wheel of the aircraft is also steerable. Not always. In the case of like the Cirrus, the SR-22, that nose wheel is not steerable. In fact, it only moves when the aircraft moves. It's kind of just freewheeling out there. In a Cessna, the nose wheel is steerable. You use the rudder pedals to control that. And as a fun fact, in case you ever get asked this question, the nose wheel on a Cessna in particular does not move during flight. So once it leaves the ground, it has some gearing and stuff in there to that the wheel has to be compressed in order to steer. So when it's in flight, the nose wheel on a Cessna does not move. However, some other aircraft, it is directly linked, and so it does move in flight. But in the case of a Cessna, it does not. So just an interesting factoid there. So yeah, there's a lot of different types of landing gear. Yeah, their main job is just to support the aircraft, so they have to be quite strong and also flexible. Um, Sometimes landing gear will also have different types of shocks, so they might have gas-filled tubes, or they might have spring shocks or something like that. And sometimes they're just uh, pieces of metal that react to the shock of landing and absorb that. All right, and the last major component of the aircraft is going to be the power plant. So it's either going to be the jet engine or a piston engine if it's on a smaller aircraft. And the power plant consists of the engine and the propeller if it has a propeller. And the propeller creates that power to overcome drag. And usually it's mounted either in the front or the back, or in the case of a jet engine, it could be even mounted on the empennage or underneath the wing or on top of the wing. There's a lot of options for this. And so the power plant creates that lift from wherever it's at. And there's benefits to having it in different places, obviously. So, but specifically, we're interested in propeller aircraft. And so in a propeller aircraft, the airfoil out front is the propeller. So the propeller is an airfoil that's what causes it to work. So it creates lift in the direction forward, and that's what allows it to move through the air. Or in the case of a pusher propeller, it creates the reverse direction. So it creates a force pushing you through the air. And so the propeller comes in two different kinds. You have the standard fixed pitch propeller, which is basically engineered with a certain pitch along the aircraft blade. Usually it changes as it goes from the root outwards towards the tip. And it's engineered usually for a very specific airspeed. And usually it's somewhere around your cruise speed. And that propeller is tuned so that it works very well at most airspeeds, but it works especially well at that cruise speed. And so you can't change the pitch of this. It's very easy to work. You don't have to worry about changing it based on your flight configuration. So that's nice. And a lot of very simple aircraft, Cessnas, have these type of propellers. The other type, which you'll see on complex aircraft, there's going to be this constant speed propeller, or what we call a variable pitch propeller. And this is going to be an aircraft, and if you go into an aircraft cockpit, it'll have a blue thing in there in the throttle quadrant, and that thing controls the pitch of the propeller blade. And so you can feather that pitch from basically 90 degrees forward. So it's going to be like it's weather vane directly into the wind. So it's not biting any part of it, all the way to the other direction, which is going to be like completely in line with the direction of the aircraft. So it's fully biting into the air. And in between these two is usually where you keep it. So you adjust the propeller based on your flight angle or your flight airspeed. And if you need more bite, you increase the bite. And if you need less, then you decrease it. And if you're flying in a constant speed propeller aircraft, usually what you do is you fly based on a certain manifold pressure. And this manifold pressure correlates to the pitch of the propeller. The propeller, in case you're curious, constant speed propeller is pitched by using pressure from oil from the engine. So the engine creates oil pressure, and that oil pressure allows you to basically there's springs inside of the propeller that pull it back to the fully weather vaned configuration. So it's completely in line with the wind. And as the engines run up, they increase the oil pressure. This puts pressure on those springs, and it allows the propeller to go into a fully feathered or fully when the propeller is fully forward and its configuration is fully biting into the wind, and it's resisting that force. So yeah, it operates on oil pressure and some springs, and so yeah, pretty cool. Usually a propeller is made of either wood, metal, or carbon fiber. And yeah, so those are the different kinds of propellers. Any questions on that? You'll see the term constant speed propeller come up a lot. And so if you see that, it just means that it can change pitch. Constant speed is kind of confusing, but yeah. All right. So there's a few other types of subsystems on an aircraft besides just the main, empennage, fuselage, wings. So inside, there's also an electrical system, flight control system, brake system. On more complex aircraft, there's even more of these systems, but we'll stick to these three for now. So there's an electrical system, and this includes the battery. It includes all the wires that connect to the lights, the flaps, flight instruments. It also includes the power system for the spark plugs, which is powered by magnetos. And so when an aircraft starts up, specifically a propeller-driven aircraft, it uses battery power to turn the propeller. And then once the propeller is turning, the propeller in turn turns these magnetos, which kind of operate like an alternator, and they create spark, which powers the engine. So in the case of an aircraft, if your aircraft runs out of battery power, the aircraft engine will still operate because it's powered by these magnetos. So as long as it's turning, it doesn't need a battery. In fact, if you're building an aircraft or it's a really old aircraft, it won't have a battery oftentimes. And so what you can do is you can just go out there and you can turn the engine manually by spinning the propeller. And this will allow you to start the engine that way. And so we call that hand propping, and you have to be trained how to do it. Otherwise, you might chop your fingers off. And so you can spin that and you can get the magnetos going. And once the magnetos are going, the magnetos actually recharge the battery, and they provide power to certain systems inside the aircraft besides just the spark plugs. So that's the electrical system kind of in a nutshell. Obviously, it's a lot more complex than that, but you don't really need to know a ton of it, just the basics of components. Flight control systems. So in the case of smaller aircraft, usually these are going to be controlled through cables and pulleys. These are connected to the yoke in an aircraft or a stick, and inside that stick or yoke is connected to wires which run the length of the aircraft to the ailerons and the elevators and the rudder, and they control what angle they're at in order to control your flight attitude. Some of the newer aircraft out there are now fly-by-wire, and basically this just means that when you input controls to your yoke or your stick, it responds by sending electrical signals to a computer, which interprets those signals and then sends those signals out to servos, which actuate the control surfaces. And this is done mostly because, especially in larger aircraft, it's almost impossible to put enough force on the stick to control that flight control surface. It's just too big, and it's too heavily weighted down by the forces on it that you wouldn't be able to move it. And so this is done by servos and fly-by-wire computers. And usually if it's going to be a fly-by-wire aircraft, the computer will also send signals back to the stick so that you can feel a lessened force, but you get some feedback from what the aileron is doing or the elevator is doing, so that you don't just kind of run it all the way to the extremes. So a lot of times they'll have some sort of force feedback on that. So like I said, that includes elevator, rudder, flaps, and the trim tabs, which are going to control how your aircraft is at its stationary position. And if your trim is changeable in flight, then you'll change that to whatever your current flight configuration is, so that basically you can just let your hands off the controls and it'll fly by itself without dipping or pitching or yawing or any of that. So those are really nice. The last major subsystem is the brake system. And this consists of the rotor on the brake and also the calipers and the hydraulic fluid and the lines. And on smaller aircraft, this is directly controlled. On larger aircraft, it's again actuated by electronics, but especially in like a Cessna, you'll have the brake pedals, and on the top of the brake pedals, or I should say on the rudder pedals, on the top of the rudder pedals, you'll have the brake pedals. And so if you do press on the top and on the pedals, it will send the hydraulic fluid to the brake, which will clamp the caliper, and it will stop that wheel from rotating. So they're pretty simple. In case you're curious, hydraulic fluid on an aircraft is red. So if you ever walk by an aircraft and there is red fluid underneath the landing gear, you might want to take a second look at that, because there's usually a problem with the brake lines. So you never want to see red fluid underneath an aircraft. All right, so now we're going to talk about some of the different design techniques as far as fuselages go. So there are a few different major types. There's the truss type, which usually is older aircraft. These are struts, stringers, bulkheads. So you'll have lines that run along the length of the aircraft that are connected to each other, kind of like, there's a picture on the next slide. It's easier to explain that way. Monocoque and semi-monocoque, like we talked about earlier. And then there's the composites. So this is some type of fiber that's placed in some type of matrix. Usually it's epoxy. And basically you can lessen the load by alternating these fibers in different directions, so that you provide strength to that entire system. And we'll talk about each of these in detail. So first, the truss type construction. So in truss type construction, you have these lines of wood or metal or something that run the length of the aircraft, and then they're connected by more, so that you end up with these sections that are all connected by these struts. And sometimes these type of constructions are also supported by bulkheads and stringers. So you'll see these bulkheads up top with stringers that kind of provide some strength in that direction as well. Again, these are usually used on older aircraft. So like this picture, it's an older aircraft, and they're not very efficient as far as like aerodynamics go, because usually they have parts that protrude out, and so the air gets in there, and they're just not very aerodynamic. They also, as it turns out, are not very strong compared to some of the other design techniques that we have nowadays. So most of the older aircraft have these, some kit-built aircraft as well. But yeah, not as strong. So most aircraft these days are going to be either monocoque or semi-monocoque, more likely, or composite. So these type of designs consist of having this stress skin that goes around either a bulkhead or some sort of stringer that runs the length of the aircraft. And the skin is what bears the weight. So the skin is stretched out to either metal or fabric or something. And it's stretched out around these bulkheads, and it provides the strength necessary to retain its shape. And so the bulkheads are the form. And then, like I said, sometimes there are these stringers that also support, gives them tensional force from front to back as well. That just helps in the overall strength. So a lot of times you'll see these semi-monocoque designs to help increase that rigidity, provide extra strength. And then the final type is composites. So a composite is something that is a resin or some sort of matrix, and then it's going to have these fibers in it. So two major examples are carbon fiber and fiberglass. So the advantages to these are that they're pretty strong, incredibly strong actually, in compressive and tensile strength. So they're very good at distributing these forces out amongst itself. So fiberglass has pretty good impact resistance, but generally it's pretty heavy. So an aircraft that is made out of fiberglass is going to weigh a lot more than something made out of aluminum or carbon fiber. So usually this will just be parts of aircrafts that are made out of fiberglass, not usually the whole thing. However, carbon fiber, you could make a whole aircraft. In fact, they're trying to make whole aircraft out of carbon fiber. So these are a lot lighter, uses carbon fibers instead of the fiberglass. So it's a lot lighter, but it has a lot less impact resistance. So it gets damaged a lot more easily, and damaging carbon fiber is a lot harder to repair than, say, like an aluminum aircraft or a fabric aircraft. Usually, these composite types are very smooth, and so they're a lot better aerodynamically, just based on the fact that they just don't have all these rivets that they need to, keep the skin attached to the body of the aircraft. And so, a lot better aerodynamically, and they perform very well. There are some downsides to composites, though. So one is that, especially with carbon fiber, if they get hit, they're very easily damaged. So these cracks can form, and they can go between the layers of the carbon fiber or the fiberglass. And sometimes you may not even know that they're there. And over time, they'll weaken that structure, and they'll cause a lot of problems down the road, especially if they cause delamination between the layers. So like you can see in these pictures up here, you can see this crack starting to form at the top. You probably wouldn't even know this crack exists, but it's working its way down through the layers, and yeah, it's just not good, because over time that could delaminate, especially if like fluids get down in there, like water, and they start breaking apart those layers. That could end up very bad. You can end up with your whole wing shearing off or something. So yeah, not good. The second picture, you can kind of see if it gets hit harder, you might see this divot, but the cracks beneath are a lot worse. You'll see some delamination occurring where the layers separate from each other. Yeah, this is pretty bad situation. If you see something like this, you really should get it checked out and not go flying. And then, you could have this third alternative where it just goes straight through. That's also very bad. So yeah, carbon fiber, great, light, smooth, but does have its problems when it comes to light impacts even. So another thing to think about is lightning protection. So most aircraft deal with lightning protection in a very simple way. They have a metal mesh that basically encompasses the whole skin of the aircraft. It's referred to as a Faraday cage, and basically just allows the lightning to travel around the body of the aircraft and exit out the other side without hurting anything inside, like the electrical system or the passengers or anything like that. Occasionally, though, if the lightning especially hits further up towards the cockpit, it could temporarily blind the pilots or do some damage to their retinas. But usually aircraft damage is very rare from lightning strikes. It's not very often that you get actual physical skin damage, but it does happen. This picture right here on the bottom kind of shows that there's this hole here, but usually the lightning just passes right through it, so no problems. And the last part of this section is going to be the aircraft instruments. So you have two different kinds of aircraft. You have aircraft that have these steam gauges, and then there's the aircraft that have the newer glass cockpits. It's all the same information. It's just how it's displayed that's different. Some people like one or the other. Personally, I don't know. I do like the simplicity of the steam gauges, but the glass cockpit is really nice because it gives you all digital readouts, so you don't have to guess at what these values are. So we're going to kind of talk about each of these. So we'll start at the top, where this kind of yellow circle is, this top left. This is going to be your airspeed indicator, and so obviously that's how fast you're going. And so this is connected to what we call the pedostatic system. And basically it has a little tube outside the aircraft that air flows into, and it measures the speed. So pretty simple. This also does adjust for the pressure of the air, and so that's also connected to a little port on the side of the aircraft that measures what we call the static pressure of the air, and so it calculates that into the equation as well. And so it's a pretty simple device, just has some like springs and gears and some other stuff in there. So this next one to the right of the airspeed indicator is what we call the attitude indicator. So it has the blue on top here, which kind of indicates the sky, and then has the brown on the bottom, which kind of indicates the grass. And sometime this will be black and white, or some other colors, but usually blue and brown is pretty common. And then in the middle here, you'll have this little airplane thing. Doesn't really look like an airplane, but it was a little dot, and then it has two bars going off to the sides. And this indicates the aircraft's nose attitude. And so as you go up towards the sky, as you pitch up, this will move into the blue region, and then as you pitch down, it'll go into the brown region. This also indicates your bank angle. And so as you bank the wings, this little triangle at the top here, this little yellow triangle and white triangle, they'll move. And so you'll get the yellow triangle pointing out towards the left or the right, depending on your attitude. And each of these lines represents a certain bank angle. So you have like 10, 20, 30 degrees, and then 45 degrees, and then 60 degrees, and then 90 degrees. And so you have all those lines indicating those. And so you can get your bank angle and your pitch attitude from that. And this is a gyroscopic instrument. So it has a gyro in there that allows it to measure those. The next one on the right of that is going to be your attitude or your altitude indicator. And the altitude indicator is another pedostatic instrument, and it works off of the static pressure off the static port, like the airspeed indicator. The airspeed indicator, though, primarily uses the pitot tube, which is that little thing that moves in the airstream and collects the speed of the air. But the altitude indicator uses the static port. And inside the altitude indicator, it has a pressurized bladder in there that is pressurized to a certain altitude. And as the altitude outside, the pressure changes on the static port, it basically calculates through some gears and some other mechanisms the difference between those two pressures, and it gives you an altitude reading. And you can adjust this based on where you're at. So it has a little window on the side that you can turn a dial, and you can adjust it to your current pressure so that it knows what the pressure is outside to give you a better reading of what is the actual altitude. So for instance, if your pressure was 30.01 inches of mercury, you dial in 30.01, and it would calculate the proper altitude based on your pressure. Then if you go down to the instrument below the airspeed indicator, we have the turn coordinator. And this is used to indicate how the aircraft is performing in a turn. So although the attitude indicator does indicate your turn bank angle, the turn coordinator is helpful in determining if you're in what we call a slip or a skid. And we'll talk more about what that is later, but basically it's how coordinated your turn is. So if your tail is aligned with the direction of flight. So if your tail, for instance, is off to the right of where your airplane is flying in a turn, it's what we call not coordinated. And so you're not moving through the air very efficiently. And you would definitely feel that as well if you're flying uncoordinated. It also is helpful if you're doing stalls in an aircraft where you're going up and you're purposely losing lift. You want to make sure that you're coordinated and you're what we call the balls in the cage. So there's a little ball down here that moves to the right and the left. And that's how you know if you're coordinated or not. If it's outside to the left or the right, then you're not coordinated. And if it's right in the middle, then you're in perfect coordinated flight. And if you're doing something like a stall, you want to make sure that that ball is in the center. Otherwise, bad things could happen. So yeah, that's what that's for. Also, this indicates what we call a standard rate turn. So it has two lines. It has the horizontal white lines. So that's your straight and level flight. And then these little white lines that are below them, that indicates 30-degree bank angle. And so for instrument flight, we do what we call standard rate turns. And it's a exact, precise degree rotation, and then it's very calculable on timer or whatever. You can calculate how many degrees you've turned based on the number of seconds that have passed in a standard rate turn. So that's what you use for that. So as long as your wings are lined up with either that one on the right side or the left side, you're in a standard rate turn at 30 degrees of bank. The one to the right of the turn coordinator is the heading indicator, and this is a gyroscopic compass. So it does precess through gyroscopic precession. You have to readjust it to the magnetic compass every once in a while to make sure it's aligned properly. And it just indicates your heading on a compass, and yeah, it's pretty simple. So the one to the right of that is going to be this vertical speed indicator, and this is another pedostatic instrument, and it indicates what your aircraft is doing in relation to its up and down speed. So how fast you're climbing or how fast you're descending. And so, if you're down at the 1, the 2, or the 3, you're descending at 100 or 200 or 300 feet per minute. And so it's helpful for planning descents. You can time your descents perfectly. You can say, all right, I need to descend at 200 feet per minute over 2 miles, and I'm going a certain speed. You can time it, and you can figure out how low you're going to go given a distance or something. So you can plan your descents, and that's pretty helpful. Especially when you're starting to do IFR flights and you're doing IFR approaches, you usually pick a vertical speed to fly so that you're always going down to the correct altitude given a certain amount of time. So those are very helpful. There's some other extraneous instruments on here. Like to the right of the altitude indicator, you have a manifold pressure indicator, which this is a constant speed propeller aircraft, and so that's helpful in determining blade angle. You also have some radio navigation instruments below that manifold pressure gauge. So the 2 below that are radio navigation, so you can shoot an ILS, or you can get a direction to a VOR off of those instruments. And then to the left of those instruments, below the vertical speed indicator, you have this RPM indicator, which is just indicating the rotations per minute of the propeller. And then over below the turn coordinator, you have another instrument which is used for navigating to radio beacons and stuff. Also, I don't think I mentioned this, but the turn coordinator is also a gyroscopic instrument. So that is the instruments in a steam gauge airplane. Any questions on that before I talk about a glass cockpit? Because once you understand this, it should be pretty straightforward. All right, so a glass cockpit. So this is what a glass cockpit looks like. Usually you actually have 2 of these displays, one on the left and one on the right. Usually one has some navigational data and stuff on it, but it has all the same stuff that this other last steam gauge cockpit had. It's just organized differently. So for instance, in the background here, you have the attitude indicator. So you have the brown and the blue with a little miniature airplane here. So you can see your pitch up and down, and you can also see your bank angle up at the top on the arc. You have that same line in each 10, 20, 30, 45, and 60 degrees of bank angle. And so there's that little triangle still up there, and that points to your bank angle. And then underneath the triangle there, actually, there we go. I have my laser pointer. So this little triangle up here indicates your bank angle. And so that'll go along this line here and indicate that. And then underneath that triangle, you have this little, I don't know, parallelogram, or I don't know, trapezoid, I think is the better word, that extends out from that. And this indicates your turn coordination. So if it's off to the left of the triangle, then you know you're uncoordinated to the left. If it's off to the right, you're uncoordinated to the right. And so you want it to be right under the triangle. You want it to be lined up with that triangle, and that indicates your turn coordination. Over here, you have the airspeed, and then you have the airspeed tape here, which shows you, your airspeed's ahead of you, and then once it goes behind you. It also has the colorations for your different V speeds. We'll talk about what those are later. And then over on this side, we have your altitude, and it has a tape here as well. And on this side, it also has a purple line. And that purple line shows you basically what your altitude will be in a given amount of time. Usually I think it's like 30 seconds or something. So the next 30 seconds, it will show you where you'll be at given your current increase in vertical speed. And so that's kind of helpful. But it's a digital readout, so you can just read it. So, in this case, it would be like 430 feet or something. And then on the right of that over here, we have the vertical speed indicator. And so that'll indicate your vertical speed, either descent or ascent. So that's pretty helpful. Below the altitude indicator, we have the pressure. So you can adjust this again for the pressure that you're currently at. And then down here, we have the heading indicator, which has a readout at the top here. So right now we're going like 340 degrees. And this also is the instrument that you use for using radio navigation and ILS approaches and stuff like that. So that's what this green line is, and it shows you're on the localizer, and that's how you can use that. This also includes your radio stack, so it shows you what frequencies you're tuned into up here and over here, your navigation, your comms. It also shows you some other like map information. Sometimes it'll even have engine instrument information over here on the left. It also shows you your distance to wherever you're going, your track, some other information for navigation. So a lot of information on one screen, which is kind of helpful in one sense, but can be kind of overwhelming if you've never seen one before. So a lot of buttons to push and a lot of information being displayed. All right, so that pretty much covers that section. Any questions on anything we've covered so far today?